A steam locomotive announced its power in public. Fire, rods, valves, smoke, and a boiler large enough to dominate the platform. The machine explained itself before it moved. The engine that replaced it was hidden behind steel panels. In 1939, four blunt-nosed diesel units left Electro-Motive's plant and began working on railroads that still trusted steam for their hardest freight. The demonstrator would travel 83,764 miles through 35 states and operate over 20 Class I railroads. But the most important thing it demonstrated was not speed, and not even horsepower. It demonstrated that railroad power could become repeatable. One crew could control several units. One engine family could serve different locomotive types. One damaged cylinder could become a shop exchange instead of a reason to disassemble an entire machine in place. And one manufacturer could sell the railroad not merely a locomotive, but an operating method. That is the real story of the EMD 567. It did not single-handedly kill steam. Railroads, traffic, capital, fuel, labor, wartime policy, and competing technologies all shaped the transition. But the 567 became the mechanical center of a system that made dieselization difficult to reverse. So why did this compact two-stroke engine succeed where earlier diesels struggled? Why did its service logic spread from streamlined passenger trains into freight, switching, branch lines, and road fleets? And after the original 567 disappeared from new production, why did so much of its architecture remain? The answer begins with a diesel engine that was not ready for the railroad. During the 1930s, streamlined trains made diesel-electric power look like the future. The Burlington Zephyr and other early streamliners showed that an internal combustion engine could drive a generator, feed traction motors, and move a train without a boiler or firebox. But a successful streamliner did not settle the question that mattered most to American railroads: could diesel power survive heavy, everyday railroad duty? Electro-Motive's early passenger locomotives used Winton 201A engines. Those engines helped prove the concept, but they also exposed the distance between a promising diesel and a dependable railroad prime mover. Eugene Kettering's 1951 engineering history describes the 567 as the result of a development program that attacked combustion, scavenging, lubrication, cooling, structure, and maintenance together. It was not a simple enlargement of an earlier engine. This distinction matters because a railroad locomotive lives inside a punishing cycle. It starts heavy trains, runs for long periods, vibrates through rough track, operates in heat and cold, and must remain serviceable far from the factory that built it. A small weakness in a marine or stationary engine could become a delayed train hundreds of miles from the next major shop. Electro-Motive therefore needed more than a diesel that produced power on a test stand. It needed an engine whose parts, airflow, structure, and repair method all anticipated railroad use. That requirement changed the order of engineering priorities. Maximum output could not come first if the result cracked, overheated, consumed its bearings, or forced a shop to improvise every repair. The locomotive engine had to tolerate long service, but it also had to reveal trouble early enough to be inspected and repaired by an organization operating hundreds of miles of track. Reliability was not the absence of maintenance. It was the ability to make maintenance predictable. Development of the 567 began in the middle of the 1930s, while General Motors was building a dedicated locomotive organization around Electro-Motive. By the end of the decade, production engines were ready for new passenger and freight locomotives. The name came from a physical fact: each cylinder displaced roughly 567 cubic inches. But that number alone explains almost nothing. The important question is what EMD built around each one of those cylinders. The 567 used an 8.5-inch bore and a 10-inch stroke. Multiply that cylinder across 6, 8, 12, or 16 positions and EMD could build a family of engines around a common basic architecture. It was a two-stroke diesel. Each downward power stroke was followed by a process that had to clear exhaust gas and refill the cylinder with fresh air before the next firing event. The engine used uniflow scavenging. Pressurized air entered through ports low in the cylinder liner, while exhaust left through valves in the cylinder head. A mechanically driven Roots blower supplied the scavenging air on the naturally aspirated versions. That airflow was not decorative complexity. A two-stroke engine cannot simply wait for the piston to complete a separate intake cycle. It must move fresh air through the cylinder quickly and consistently. Poor scavenging leaves exhaust behind, raises temperature, contaminates the next charge, and destroys the advantage of the two-stroke cycle. EMD engineers worked through port shape, air flow, valve timing, piston temperature, fuel injection, bearing loads, and structural stiffness as parts of one problem. Kettering's paper is valuable precisely because it does not describe the 567 as a flash of inspiration. It describes an engineering campaign, failures observed, mechanisms studied, parts revised, and results tested. The 45-degree V layout kept the engine narrow enough for locomotive packaging. The crankcase, cylinder banks, blowers, fuel system, lubrication system, and generator connection became a compact power plant that could live inside a car body instead of defining the outside silhouette of the locomotive. This is where the visual contrast with steam can mislead us. Steam placed much of its mechanism in view. The diesel-electric locomotive concealed the engine and transferred the drama to systems the passenger rarely saw: air flow, fuel delivery, generators, traction motors, controls, and shop procedures. And the most consequential design decision may not have been the firing cycle at all. It may have been the decision to treat the cylinder as a replaceable assembly. On the 567, the liner, piston, connecting rod, and cylinder head elements could be handled as a power assembly. A shop did not have to treat every internal failure as a reason to rebuild the entire engine inside the locomotive. A suspect assembly could be removed, inspected, exchanged, and rebuilt away from the locomotive while the rest of the machine returned to service. That sounds like a maintenance detail. In a fleet, it becomes economics. Railroads do not earn revenue because an engine is elegant. They earn revenue when locomotives are available to move trains. Every hour spent waiting for a custom part, a specialist, or a long teardown is an hour when the railroad owns machinery that is not transporting anything. Steam shops had developed extraordinary skill in maintaining boilers, running gear, valves, rods, wheels, and appliances. But much of that practice was tied to particular locomotive classes and to heavy repair facilities built over decades. Hare's documentation of the Southern Pacific Sacramento shops shows a vast industrial institution organized around fabrication, fitting, rebuilding, and the accumulated craft structure of steam-era maintenance. The 567 did not eliminate skill. It changed where skill was applied. A steam-era back shop could be a railroad inside the railroad: foundry, forge, wheel shop, boiler shop, machine shop, stores department, laboratory, and training ground. Its strength was the ability to keep a diverse fleet alive by making what could not be ordered. Its weakness was that so much knowledge and capacity belonged to a specific place. Standard diesel components moved part of that capability into a supply network. The manufacturer could revise a part, publish a service instruction, and distribute the change across many railroads. The railroad gained repeatability, but it also accepted a deeper relationship with the builder. Instead of fabricating every solution around an individual locomotive, the diesel shop increasingly diagnosed a system, exchanged standardized components, and sent assemblies through repeatable rebuild processes. Electricians, machinists, inspectors, parts planners, and service representatives became part of a new maintenance ecology. This transition was not instant, clean, or identical on every railroad. Old facilities remained useful. Steam and diesel worked side by side. Capital budgets constrained what management wanted to replace. But the direction was clear: standardization allowed knowledge, tooling, and inventory to travel across a fleet. EMD had built an engine that could be serviced as a product family. Now it needed to prove that the family could move mainline freight. Passenger streamliners were persuasive, but freight was the test that could change the industry. Freight trains were heavy, schedules varied, routes crossed mountain grades and long distances, and railroads already owned steam locomotives designed for specific kinds of work. Electro-Motive's answer was the FT demonstrator, number 103, an ABBA set of 4 units. Between November 1939 and October 1940, it worked across a national demonstration tour, operating on 20 Class I railroads in 35 states and accumulating 83,764 miles. The tour turned a sales argument into operating evidence. Railroad managers could see the locomotives on their own grades, with their own trains, under their own rules. They could compare turnaround, servicing, train handling, and availability against familiar steam practice. This was especially effective because railroad practice is local. A locomotive that performs well on level track may behave differently on a mountain district. A train that looks impressive in a brochure may expose cooling, adhesion, or braking limits in real service. By moving the same demonstrator across many properties, Electro-Motive created a common reference point while letting each railroad observe it under familiar conditions. The tour was marketing, but it was marketing structured as field evidence. The legend later became cleaner than the history. It is tempting to say the FT arrived and steam died. That is not what happened. World War II shaped production. Government priorities limited which locomotive types could be built and where they could be assigned. Railroads made different decisions at different times. Some had abundant coal, modern steam fleets, strong shop traditions, or capital constraints that slowed dieselization. But the FT tour changed the burden of proof. Before it, diesel freight power had to prove that it belonged. After it, a railroad choosing new steam power increasingly had to explain why it was rejecting a system that could be tested, ordered in units, combined for different train weights, and supported by a growing manufacturer network. The FT's engines mattered. Yet the train moved because those engines were embedded in an electrical machine. And the proof did not end when number 103 returned from the tour. Orders, wartime production, and later locomotive families converted a demonstration into installed capacity. Every new fleet added mechanics who knew the equipment, stores departments that carried the parts, and managers who could compare actual results. The more railroads learned to operate diesel electrics, the less risky the next purchase appeared. This feedback loop, not one spectacular run, is how technical credibility became institutional momentum. The 567 did not drive the wheels through a mechanical gearbox like a truck. It drove a generator. Electricity then flowed to traction motors on the locomotive's axles. This arrangement separated the engine's useful operating range from the speed of the wheels. The diesel could run where it produced power effectively, while the electrical system managed the enormous torque required to start a train and the changing demands of acceleration and grade. That is why the phrase diesel locomotive is incomplete. The decisive package was diesel-electric. The engine, generator, traction motors, control system, cooling equipment, and locomotive body had to work together. A reliable prime mover attached to poor electrical equipment would not create a reliable railroad locomotive. A good generator with an engine that could not survive the duty cycle would fail for a different reason. Multiple unit control extended the system beyond one locomotive. Several units could be coupled and controlled from one cab. A railroad could add or remove units to match the train instead of building a separate giant steam locomotive for every extreme duty. This modularity affected more than horsepower. It affected scheduling and risk. If one unit developed a problem, the consist might retain useful power. A locomotive family could be distributed across passenger, freight, switching, and road service while sharing parts and service knowledge. Not every early diesel consist delivered perfect flexibility, and railroads still face trade-offs in gearing, axle load, adhesion, electrical limits, and maintenance capacity. But the organizing principle was powerful: build capability from standardized units. The same logic existed inside the 567 cylinders, inside the locomotive, and across the fleet. There was another advantage to this layered modularity: it gave the railroad more than one scale at which to respond to failure. A power assembly could be exchanged inside an engine. A unit could be removed from a consist. Another compatible locomotive could be assigned while the first entered the shop. None of these options made failure harmless, but each reduced the chance that one damaged component would immobilize an entire transportation plan. That is an infrastructure benefit, not merely a mechanical one. The Second World War interrupted the peacetime market and accelerated the importance of railroad capacity. Railroads had to move troops, raw materials, fuel, food, and finished weapons through a network already under strain. Wartime production policy did not simply allow every railroad to buy whatever it wanted. Manufacturing capacity and locomotive allocation were controlled. Steam remained indispensable. Diesel switching and selected road applications expanded where policy and production permitted. The larger transformation came after the war. Post-war railroads were not choosing between a brand new diesel system and a brand new steam system on equal terms. They were deciding what to do with existing steam investments while traffic patterns, highways, airlines, labor relations, and capital markets changed around them. Some steam locomotives still had years of useful life. Some shops represented enormous sunk investment. Dieselization therefore advanced through purchases, retirements, reassignment, and rebuilding rather than through one national switch. Railroads faced worn equipment, changing labor costs, deferred investment, and pressure to move more traffic with predictable resources. EMD could offer locomotive families built around common engineering, service documentation, replacement parts, and a growing field organization. The 567 appeared in streamlined F units, passenger E units, switchers, and the road switcher designs that made diesel power less specialized. The GP7 and GP9 did not need the visual theater of a streamlined passenger train. Their value was functional. One locomotive form could handle road freight, local work, branches, and transfers with fewer boundaries between assignments. This was a profound change in how a railroad could think about motive power. Steam fleets often contained many classes optimized for particular work, each with its own history of modifications and shop knowledge. Standard diesel families promised fewer unique systems, broader assignment, and a supply chain tied to continuing production. Road switchers made the contrast especially visible. A locomotive did not need a polished passenger car body or a freight-only identity to justify itself. It could arrive on a local freight in the morning, switch an industry in the afternoon, and cover another assignment when traffic changed. The point was not that every GP locomotive could do every job equally well. The point was that the boundaries between categories became easier to cross, allowing management to treat motive power as a pool rather than a museum of specialized classes. Again, the promise was not automatically fulfilled. A railroad could mismanage diesel maintenance just as it could mismanage steam. New electrical and control systems demanded training. Early components had weaknesses. Standardization could create dependence on a manufacturer. But once enough locomotives, parts, manuals, shops, and trained workers existed, the network reinforced itself. Buying another compatible unit became easier than preserving a shrinking island of incompatible practice. That is how a machine becomes infrastructure. Steam locomotives did not disappear because engineers suddenly forgot how to improve them. The final generation of American steam power included machines of extraordinary capability. The problem was the systems surrounding each mile. A steam railroad required water, fuel, ash handling, boiler inspection, firebox work, running gear attention, roundhouses, specialized tools, and the labor structure developed around those needs. A diesel railroad required fuel and maintenance too, but it redistributed servicing across longer intervals and different facilities. The comparison varied by railroad. Coal price, diesel fuel price, route profile, traffic density, shop condition, financing, and fleet age all mattered. This is why simple universal claims about fuel savings or cents per mile are dangerous. A number drawn from one railroad or one promotional comparison cannot describe the entire country. Capital cost complicated the picture further. A railroad could recognize the operating appeal of diesel power and still delay a purchase because usable steam locomotives were already paid for. Conversely, a railroad facing worn steam power and expensive shop renewal could see dieselization as a way to avoid rebuilding two systems at once. The same technology therefore produced different timing on different properties. A credible history must explain the direction of change without pretending every decision followed the same spreadsheet. What can be said with more confidence is that diesel-electric fleets offered operating flexibility that steam struggled to match as a system. Units could be combined. They could run in either direction without turning the entire consist. They could share standardized components. They did not require a fire to be built before work or maintained between assignments. A railroad could redesign shops around inspection bays, exchange assemblies, and plan component flow instead of preserving every part of the steam support landscape. The change also carried human cost. Crafts built over generations lost status or disappeared. Communities organized around steam shops faced layoffs and reconstruction. Corporate efficiency is not the same thing as social neutrality. Nor did dieselization remove heavy industrial labor. It replaced some kinds of heat, ash, boiler work, and custom fabrication with fuel system work, electrical troubleshooting, engine rebuilding, cleaning, inspection, and parts logistics. The new shops could be cleaner and more linear, but they still depended on disciplined workers and expensive equipment. The revolution was organizational before it was effortless. The 567 helped railroads move more of their maintenance burden from the trackside spectacle of steam into controlled industrial processes. That made the locomotive less romantic, and, for management, more predictable. Predictability is difficult to photograph. It is also one of the most valuable things an infrastructure system can produce. By the 1960s, the original 567 family was reaching the edge of what EMD wanted from its displacement, power, and production architecture. New locomotive ratings and market competition pushed development forward. In 1966, the 645 family replaced the 567 in new production. But replacement did not mean that EMD discarded the entire idea. The 645 enlarged displacement per cylinder while preserving much of the two-stroke, uniflow scavenged, service-oriented lineage. Later EMD engines continued the pattern, a locomotive prime mover designed not as an isolated object but as one element in an electrical and maintenance system. The continuity became visible in preservation and rebuilding. Some later 567 crankcases could use 645 series power assemblies under specified conversion rules. The exact compatibility depends on crankcase type, water manifold configuration, camshaft details, governor settings, and EMD service instructions. It is not a universal drop-in promise. This long service life also changes how we should define obsolescence. A design can become obsolete for new production while remaining rational to maintain in a locomotive whose frame, generator, trucks, and mission still have value. Replacement depends on the whole asset, not the birth date of one engine family. Museums and tourist railroads make this continuity visible, but similar logic has always existed in industrial fleets. A supported machine may outlive the market that originally created it. That qualification is important. Enthusiasts often describe old EMD engines as if every part from every generation can be exchanged. The real achievement was not magical interchangeability. It was a design culture that valued controlled evolution, service documentation, and family resemblance strongly enough that old machinery could remain supportable. Surviving 567 powered locomotives now operate in museums, tourist service, short lines, and specialized industrial roles. Their continued movement is not proof that old technology is always better. It is evidence that maintainability, part strategy, and institutional knowledge can extend a machine's useful life far beyond its original sales era. The 567 left new production catalogs. Its logic did not leave the railroad. Return to the steam locomotive at the beginning of this story. Its power was visible. The 567's power was concealed, not only behind a car body, but inside a network of standards. The cylinder dimensions mattered because they supported a family. The two-stroke cycle mattered because EMD learned to control air, heat, fuel, and structure together. The power assembly mattered because a fleet earns money when locomotives return to service. The FT mattered because it carried the argument onto the railroad's own ground. Diesel-electric transmission mattered because engine power had to become controlled tractive effort. Multiple unit operation mattered because railroads needed scalable capability, not just a single heroic machine. And the shops mattered because no transportation revolution survives on a demonstration run alone. The EMD 567 did not make America great by itself, and it did not erase steam with one perfect technical victory. It helped build American capability by making heavy transportation more repeatable, common engines, common parts, shared training, flexible consists, and maintenance organized around availability. That repeatability changed what railroads could promise factories, farms, ports, cities, and military logistics. A train was not merely a locomotive pulling cars. It was a scheduled claim on national capacity. This is what happened to the 567. It was replaced as a model, absorbed as a lineage, and preserved as an operating idea. The loudest machine in railroad memory may still be steam. But the machine that made the new system durable was working behind the panels. And once the railroad reorganized around it, there was no simple way back.